So I would like to answer a few questions here. Arvind Kundu. So how to use different surfactants or keeping ligands control shape of the nanocrystal, how the basic of this. So a particular ligands has to bind a particular surface depending on the atomic arrangements of the surface. Depending on the atomic arrangement of the surface, then the ligands bind. So if you change the ligands, you can generate the new facets. So next is Shraddha Sapru. So how do we know the ammonium cations results in the cube structure? No, that's for our experience. We have shown that when the primary ammonium ion are taken, it retains always the cube structure. It stabilizes the 110 or 002 facets. So that's what it is. So as I was talking, that the science is what we found mostly. What is the results we found? Then we investigate like this nature process. We are studying it out. So once we found these are stable, we checked out and we found that everywhere there is an ammonium ion that gives the cube structures. So next questions I would like to talk about how to identify ligands for a given facets. Is there any rational understanding? This is a bigger question where also, as I was talking about, we also found these particular ligands we used are accidental. We are searching something, and but we came out with a different ligand. We are searching something, we come out with a different ligands. And we found that ligands has been given with a bigger size. Once this is given a bigger size, it could stabilize that 020 or 200 facets. It didn't stabilize any facet which has been cube as like 110 or 002. So I will go for the next question. TM is a 2D projection of 3D crystal. This is for Ohin Roy question. How do you determine the three models? Well, it has to go for ACM. Fine. This has to go for ACM. But in this particular cases, once the best way to look at it out is the hard of STM images. If you go for hard of STM images, you got that clue. And otherwise, what happens? You take the models from the HRTM images. How many HRTM images you can collect, the way it is viewed, and we project from those models. We try to simulate what should be the set. For example, if it is a disk, it has two orientation. Either it will be vertical or it will be horizontal. If it is a spherical particle, you could see the HRTM images, you could see the many orientations are there. If it is a cube, you could see only one facets are coming up. But here, particularly in cases where 12 facets are there, we found that it has three orientation. All the three orientation we considered, and we found if it is an 110 view, all possible 110 view model we take it. This is what we have done this modeling. From this modeling, we have done the structures. So next, why only size changes with temperature, not shape? Well, this is a bigger question. Shape dot changes. As I was showing that when we go beyond 220 degrees, the shape has been changed. But you should understand that this is the ligands who determine the shape also. So if the ligands remain same with the temperature, the size has to be changed. This is a big opening of this field that if at all you are given a 5 nanometer particles wants to grow for 10 nanometer, we don't have any chemistry that can make us a 5 nanometer particles to that of the 10 nanometer. So that is what for 5 nanometer you have to do one reaction, and for 10 reaction, for 10 nanometer also you have to do another reaction. For 10 size particles you have to do 10 reaction, and these are so fast. These moves so fast that you cannot quench it. For example, if you make a card selenide, nanocrystals. So once you inject and take out the sample from time to time, you could see that the size of the particles that have been changed. But unfortunately, in case of the perovskites, you don't see those. Once you inject, it has been finished. That part has not been solved yet. But that's what the protocol, which has been responsible for cube. If you use this protocol for different temperature, you see only that cube, not the others. Once you want to see, you have to go beyond certain temperature where the ligands and the surfaces would not be able to stabilize. I hope I have answered these questions. So next question is Ohin Roy. This question is already I answered. So then next question is, what are the practical applications of these nanostructures? Again, nanostructures gives of faking. Once you got a nanostructures, you can help it for faking. So once you have a faking of these nanostructures, you have a self-assembly. Once you have a self-assembly, you have a device one. So the second thing is that you have a different facet, you have a different adsorption. Suppose cube has a single facet, so if you have a other facets, you have a different adsorption ability. So once you have a different adsorption ability, you have a different catalytic ability. This is the one thing you could see it out. These are different with the different shape of the nanostructures. Moreover, suppose if you were to like a perovskite systems to put a gold on it, a plasmonic gold, it could not be successful yet. There is no such structure which has been reported where perovskites can be directly connected to that of the gold. So that's what you need a new facet might be, because the cube has only 6 facets. So you might have a new facet to be created where the lattice spacing will be same as that of the, or it will match with that of the gold, leading to turning out to be heterostructures. So then I have a next question that is called from Subodhi Panda. I need your suggestion whether we can achieve such direct pattern using anti-solvent method, and can polymer protein help in achieving the same for development of CSPBPR perovskites at room temperature? Well, this is the question where one has to understand that we don't use polymer at this stages. We simply do the non-coordinating solvent with a limited number of organic ligands on it, which we desire. One has to understand that why, how they will form on the polymer or protein at the room temperature. But as you understand that the cesium is here is one of the culprit. Cesium, something is that quickly reacts with moisture and that of the polar solvent. So this destabilize the structure. Destabilize the structure means the phase has been destabilized. That is what we have a difficulty in the adopting any of the system for these materials. Well, so next question here is, are you targeting any application of how to making such nanocrystals? So this is from Vishal. So this is the question which has been, every day also we think that what kind of applications we are doing it. But we are chemists. We love the reaction flux at this stage. We focus, as I was showing in the beginning, the cutting edge research in the field, which is lying, which is vacant. We need to understand that we have to get in out. Yeah, for applications, we received a project on the nanoemissions for making LEDs. We'll try to develop that for light emitting devices at this point. Sushant, next question is from Sushant. How you tried such strategies on team-based perovskite nanocrystals? How do you account for stability of these materials? Well, so at this point, we are expanding this with methyl ammonium, or we are planning for the double perovskites. We have not yet done with the team-based perovskites. But as I was talking about, you need a certain temperature to stabilize this. I'm not sure because we didn't work with the team-based. Our strategy is to focus one particular issue and get deep into. This is the way we saw that why these are not other than the cube. So we try to understand that. We have developed that facets can be tuned. The new nanocrystals without compromising the optical properties can also be developed. So next question is why is bromide precursor you have taken alpha ketobromide? Has it any impact? This is the bigger question that why is a we have taken it out. So we are actually searching for something else. So we are searching benzoyl bromide. It has been done by Electron group to synthesizing of all the perovskites. Once we were searching this, and someone who was working on this project, he found from his friend this particular, which is 2CH2 group extra. So we tried this, and we saw it's a miracle. It was you know, it's opened up. It's opened up the new facet. The perovskites with the new facets can be stabilized. This is what it is an accidental. It turns out to be reality. Well, the next question from Jafar: by which method these type of crystals? This is what we do. We have done in the reaction class, as I was talking about. Small crystals, every small crystal, which is to be less than 50 nanometer or 10 nanometer, has to be on the bottom of your cross. The atoms and the crystals to be connected. This is the way it is done in the reaction class. So for physical methods like CVD and others, you cannot make such a small crystals. I believe I have answered Jafar. So the next question is from Shorav. Can we specifically define the synthesis of specific crystal formation, or it is a random phenomenon? Well, from the beginning, I saw this one from the comedy, the pictures of Mr. Bean, that we just mix up the chemicals, or we went to the school where we try to understand that something mix up, something will come up. So in the nanochemistry, if you saw it out, most of the things are going hit and trial. So once you get something, you try to understand, like we study the natural process. And the field is too premature at this stage. So that's the way it has been done at this point. So as if you look at it out the phenomenon, two types of ligands we design, it gives two shape of the nanocrystal because it works. We have to try, and from this we understand the size where it fits is more important. So next question is why excess ligands is used in facets? Can we don't calculate the concentration needed for this? Yes, we can calculate. Excess ligands are there. Ligands has several role on the making the nanocrystals, because ligands, if you have a bind strongly, then you cannot grow. If you bind loosely, it grow faster. So you should have make an equilibrium where the ligands and bonded and outer ligands, they make a dynamic equilibrium on the surfaces. That one has to maintain always. For this reason, there should be an excess ligands on the surface, on the bulk, on the solid. If there will be an excess ligands, then always you will find some ligands on the surfaces that stabilizes, that stops also mixing with the other particles or the agglomeration. That is what ligands are always being taken in the higher concentration. Next question is Shamnath Das. Can this structural evaluation be seen for red or violet emitting nanocrystals? How stable these nanocrystals are with different facets under ambient condition? This is a good question. When this work we are doing, it was also in our mind, but we are hurried to release this work because it was delayed because of the lockdown. So we did try it on this, but this chloride one was not so beautiful, but the new facets can be fun. But as I was talking about, this particular ligands fit in the size of a particular facets of bromide. Once you come out to the iodide and that of chlorine, you might have to tune the ligand size so that it can stabilize this. In iodide, we didn't try on it. So next question, this is Karnveer Singh. What is the SB ratio of this one micrometer bigger than one in the images of the nanocrystals? Well, this is typically we do not work on this. This is something we got it. We typically do not go beyond few nanometers. we get it because we just get it. That's all. So this particular cases, what happens? These bigger crystals, they weren't so big, and bigger crystals are poor dispersity. And you cannot see that clearly in the images. That's what I have shown this inverted images. But the beauty of this particular case was it was killing all the small particles, which is a non-Oswald ripening type. This is just eating. In Oswald ripening, what happens? The smaller particles get smaller, bigger particles get larger. But it was not happening like that. It was just killing everything. So this is a new fundamental phenomenon. That's why we have introduced. But typically, beyond 20 or 30 or 50 nanometer, maximum 100 nanometer, we can deal with. Otherwise, they get precipitated. So next is question is, can we make porous nanocrystals using your approach? Typically, no, we don't deal with the porous nanocrystals. This is what we do with the crystalline materials. We do as the crystalline materials, and that we beat in high temperature. I think entire thing we store in the crystalline. Porous something, I'm not sure it can be made with such a good monodispersity. The next question is that why cesium is used here? Well, cesium is the largest, several times I told that this is the largest atom in the periodic table. Cesium is the largest atom on the periodic table. So we use the cesium here because it fits inside that tetrahedral setup, tetrahedral arrangements to make the tetrahedral, protect the tetrahedral from tilting or collapsing of the crystals. That is what the largest size atoms, which is cesium, has been used. If you want to go beyond that, then you have to use methyl ammonium or butyl ammonium or something bigger cesium for this particular cases. Next question. By changing the shape and size, the area of application will also be changed. In this case, would the surface area affect accordingly? Well, first of all, the facet or the surface, it is different. Surface means it is an adsorption capacity, it changes. And the surface area is always calculated a particular mass, how many number of particles you have used for this. Suppose you have a same size, obviously the surface area would changes. But if you have a different size, this is also relative how it has been changed. If you have a smaller size, the overall surface area will be larger in any set. If you have a larger size within the same particular mass of the materials, then it will be a less. This is what the surface area related effect of these nanocrystals. Next question, Somnath. What are the change in electronic coupling among the perovskite quantum dots you expect when all cube from a superlattice compared to the superstructure presented in the last slide? Well, these are cubes we have not studied. The hexagonal structures, what we put it out, dodecahedron, we are trying to get the supercrystals. Regarding the superlattice, in these cases, this is just our beginning. We just prepared this type of materials. We have to study some more on it. So if I understand, you are asking the superlattice of these 12 faceted nanocrystals. That's what I'm talking. But the last slide was the larger size nanocrystal. How you don't get any supercrystals or superstructures on that. Next question. Stabilizing certain phases didn't hamper their structural and chemical morphology. Well, chemical morphology we saw it does not hamper at these stages, but sometimes like as I was talking that if there is an polar some entity on it, then the compositions would be changed. But in these cases we didn't say this one. And regarding structural, you talk about the phase on this. No, absolutely no phase change has been observed on these materials that we saw there. Phase change means you lose the optical activity. From the reaction flux, if you put the UV light, you will be able to know about it. So what are the future of perovskite nanocrystals? So I'll let it out the questions of the future of perovskite nanocrystals. These are big questions. What will be the future? As you know that the highest solar cell efficiency is also perovskite nanocrystals, and also people are trying to make the LEDs because these are all near unity quantum efficiency of the materials. Regarding the stability is a question with the time, with the time this is going to be solved, because we need a robust surface, robust capping of these materials. And because of the newly emerged, not much science has been known. It has not yet been uh, studied yet. Regarding the other aspect there, let us study the science aspect, because as recently Prasant Kamat was talking, as you have heard probably, that last talk it has been happened in India. So no one also imagined that quantum dot will be on your display. So now the quantum dots, which has been in the 30 years before, now in the TV panels. So that is the cases. So it might also have a applications in the future, and we will be able to wait and see. So next is the question is, what is the minimum yield of the materials? Well, so this is something, the cesium has been treated. Cesium has been used as a rate determining step. So the amount of cesium you get the yield compared to that. But the problem is here, if you want to high yield, then the issues are viscosity is losing. If you want to the all particles looks like same, then you have to use in the small scale. We do in the 25 ml or 50 ml class. If you go higher up, then the particle size will be reduced. But that's what you need it, what kind of application you want. You can prepare more of these materials. So next question is, what is the magnetic behavior of these materials? Well, these are the, at this point, we have not studied. We need to have introduce a magnetic dopant on it to see the magnetic behavior of these materials. At this point, we didn't find this particularly. There are reports on how the methyl ammonium moves and other things, but in case of cesium, we didn't find any such behavior. So next question is that, does heating rate affect the crystal forming? So as I was talking about, this is heat. This is the temperature. When coming out red, that indicates that in particular reaction, the heat has been changed from one time to other time. But the unsolved part of these materials are there. Once you inject, it has been finished. Once you inject, you have to go for ice cold. Sometimes if you do not ice cold, that then what happens now, the phase has been changed. That is what it is the matter of how you are doing it. So basically, there is no rate question arises here, but different temperature, yes. If you put it out different temperatures, then the size, sometimes the shape would also change. So next question: if solubility product play any role while selecting the material? If we want to switch from cesium to other in the periodic table, this solubility product is a secondary question. It helps in solubilizing of your salt. But if you want to cesium, why it is has been taken? Because cesium is the largest, more the size of your, this is monovalent cations, it stabilize your system. That is what cesium. If you have a reduce the size of this, particularly A size or plus size, reduce the size of this material of the ions, your system will be more unstable. That is what it's very difficult to stabilize the system or getting this type of properties. And the next question, is the synthesis of perovsky nanocrystal specific to organic medium or can be performed in aqueous medium? It is performed in any medium, it can be done. But organic medium, you do it out because of high temperature. High temperature helps you making the crystallinity. So if you do it out below 100 degrees, then your crystallinity will be poor. So you have to do the temperature as high as possible. That's what maximum temperatures are done within 200 to 300 nanometer, degree centigrade. But regarding the water cases, there are several reports are there, but not on perovskites. But if you go for perovskites in water, I was talking, the cesium is going to be losing. It has to be coming out. It reacts with the polar sulfate, and that is what the entire structures will be collapsed. So that is what it has been always high temperature, and for high temperature you have to use organic sulfate. And the question, possibly this is the last question. Have you tried any biological applications? The biological applications of these materials are not yet been started. The reason is that for biological application, you need these materials to be robust in water solubility. But as I was talking from the beginning, at this point, these materials are mostly in the organic solvent. These are soluble. Once you try to take it out, once you are try to take it out, then put in water, then you lose the crystals. The emission is dim, as well as the crystal structure has been done. One more question I can see here, is any top-down approach available? Top-down approach, as I was talking, for any nanocrystals, if you want to see the quantum confinement, like 1 nanometer to 5 nanometer, 1 nanometer to 10 nanometer, the ideal is the solution method, bottom-up approach. If you want to top-down, reaching to that particular size is very difficult. And if you want to also get it out, you will not get the beautiful properties. Particularly surface ligands are necessary to stop the dangling bonds and to get it emission of these materials.